In this video, we're going to talk about limit points in topological spaces. So our definition, let x tau be a topological space and let A be a subset of X. A point X in X is a limit point of the set A if every open set containing X contains a point of A other than X. So in other words, here's our set X, our subset A, and a point X. X is a limit point of A if for any open set containing X, that open set U contains some point of A other than X, A not equal to X. So this is actually the same definition that we had for limit point in a metric space. The limit points of A are denoted A prime, as before, and A is also sometimes called, or A prime is also sometimes called the derived set of A. So for a couple examples, first of all, since, as we said, any metric space is also a topological space, where the elements of the topology, where the open sets are just the open sets that you had in that original metric space, all of our previous examples of limit points still apply. So for a couple of quick reminders, if we have like the real numbers with the usual metric, then the set of limit points of the rational numbers, Q, remember, is the rationals. The limit points of that set is the entire set of real numbers. Why is that? If we take any X in the real numbers and take an open ball or an open set containing X, then in the usual metric, any open set also contains an open ball of some positive radius, X plus epsilon, X minus epsilon, and we know that between any two real numbers there is a rational number. There exists some Y in the rational numbers and in, say, this X to X plus epsilon. So that means Y is not equal to X, and so yes, every real number is a limit point of Q, the set of rational numbers. Whereas if we look at the real numbers with the discrete metric, we recall that the discrete metric has defined that the distance between 2 points is either 1 if the points are not equal or 0 if the points are equal. So for any X in the real numbers, the ball centered at X of radius, say 1/2, contains only the point X. So that is an open set in the discrete metric, and therefore for any element X, X is an open set containing X that contains no other point of Q, and therefore the set of limit points of Q is the empty set in the discrete metric. Here's one more example. Now here's a new one that isn't one we looked at before. We did show in a previous video that the collection of sets, empty set, the set containing B, the set containing B and C, and the set containing A, B, and C is a topology for the set A consisting of the elements A, B, and C. So what are the limit points of the set A, B in the topological space A, S? So I would like you to pause and think about this with the definition of limit point for a moment, and then we'll talk about it. Okay, so what are the limit points of the set A, B? So let's look at these one by one. So, here are all the possible options. So is A a limit point of the set A, B? Well, we have to look at each of the open sets containing A. We see that this is the only open set containing A. So A, B, C is the only open set containing A, and therefore, that's the only open set containing A. We need to show that for any U open such that A is in U, U intersected with the set of interest A comma B minus the point A specifically is not the empty set. That would be showing that A is a limit point of A comma B. Well, is that true? Yes. So A, B, C minus the point A intersected with the initial set A comma B is not empty. B is in there. And therefore, A is a limit point of the set A comma B. Now, is B a limit point of A comma B? Well, here now we have more open sets to select from. So the set containing just B is an open set containing B. So the set containing just B is open, and the set B minus that point intersected with A comma B is the empty set, and therefore B is not a limit point of the set A comma B in this topology. Lastly, is C, that's the last element in the overall set X, a limit point of the set A comma B? Well, let's see, what are the open sets containing C? Our open sets containing C, open sets containing C are the set BC and the set ABC. B comma C and A comma B comma C. So each of these contains a point of the set A comma B other than C. So that means that, and what is that point? Each of these contains the point B, which is not equal to C. And so, therefore, it is the case that C is a limit point of the set A comma B. So in this topology, the limit points of the set A comma B are the set A comma C. A is a limit point, C is a limit point, B is not. Here's a theorem about closed sets and limit points that will be familiar to you. A subset A of a topological space is closed if and only if it contains all of its limit points. Now we proved this for metric spaces, and partly we proved this in the notes and also in the homework, one direction in each place. So I'm actually going to have you prove this again for homework, the whole thing. And there's different ways you can approach this, but note you have to do it in a topological space. In other words, we can't use metrics. We can't use a ball centered at x of radius epsilon. We can't use the idea of distance. So we have to prove this completely in terms only of open sets. And in order to prove this, we don't absolutely need this lemma, but it's a useful lemma anyway, and it is useful for, I would say, one direction of this theorem. So you can use this lemma if you wish, and I also expect that we'll use this lemma going forward in the course. A subset A of a topological space x tau is open if and only if for each x in A there is a set U in tau in the topology such that x is an element of U and U is a subset of x. So let's prove this lemma that will be useful both for proving the theorem above and more generally. So going in the forward direction, suppose that A is open, and remember in a topological space, that's equivalent to saying that A is an element of tau. It is one of the elements of the topology. We want to show that for each x in A, there's some open set U such that x is in U and U is a subset of A. Well, this direction is immediate, right? So therefore, for any x in A is open, X is an element of A, which is a subset of A. Any set is a subset of itself. And because A is open, that means it's in the topology tau. And so, the one direction is kind of immediate, just understanding the definition. Going in the reverse direction, suppose that it's the case that for any X in A, it's the case that there exists some open set, let's call it U sub X, because it's an open set containing X, such that X is an element of U sub X, and U sub X is a subset of A. So suppose that's the case. Then our claim is that A is equal to the union of all these U sub X's for all X in A. So to show that little piece, to show that A is a subset of that, well, for any X in A, we're already saying that there exists this U sub X such that X is in U sub X. That's how U sub X is defined. So X is in the union of these U sub X's. And that tells us that, yes, A is contained in the union of the U sub X's. For the reverse inclusion, U sub X is a subset of A for each X, and therefore the union of these subsets of X is also a subset of X. So, okay, great. So we know that A is the union of these U sub X's, and now, by definition of a topological space, the union of any collection of open sets is open. So because A equals the union of these UX's, and each of these UX's is open, therefore is open. A is open. And so we've proved both directions, that a subset A of a topological space is open if and only if for each X in X, there's a set U in T such that X is in U and U is a subset of A.